So now we're going to look at what happens when motion goes in a circle instead of in nice straight lines. This leaves us with talking about distances as angles and things called angular velocity and tangential velocity. Bringing on some new terminology, new vocabulary, and some symbols that are new and units that are new. And we were talking about distance with a D and meters, and now we're going to talk about rotational angle, which has a theta and radians. And we have velocity in a straight line in meters per second, and for angular velocity, we're going to have radians per second. Now, tangential velocity will be in meters per second, and we'll have arc length in meters. So that's the distance around the circle. So some of the things kind of stay the same. A little bit about the rotational angle. So this is the distance you go around the circle in terms of an angle. So from 0 to 360, we're going to talk in radians. So it's from 0 to 2 pi. You'll have to convert between the two of those. And then we need to talk about the conversion between a linear displacement. I moved this far, but something was rolling. What does that equal in an angle? So here's one example. We want to know how far does a bike with a wheel with a radius of 0.32 meters travel when the wheel goes 1/2 of the way around. So really short distance. You can imagine the wheel just turns halfway. How far do you think the bike is going to move in a linear distance? And so you set this up where our angle is just pi, halfway around the circle, and we're looking for arc length. So we're looking for kind of the chunk of the circumference equivalent to pi with this particular radius. And the equation is the angle is equal to the arc length over the radius. You plug your information in, keep things in radians with pi, and we get that we went 1 meter in distance for a half turn on a bike wheel. And the equations aren't all that complicated. You just kind of have to think in terms of circle and pi. And if you're having trouble imagining that, think about how the clock moves from 1 o'clock to 3 o'clock, or we're going to do the second hand from 1 to 3. And it goes some distance, which would be s. And we want to find that angle. We would use the arc length over the radius. And so we get that distance is theta r, or s is theta r. We plug that into our velocity equation, and we end up with the idea that omega, which is our angular velocity, that's that curly w, is the angle divided by the time. Should make sense. That's distance over time again, but it's in terms of angles. And then we can go back and look at the tangential velocity, which would be the distance the bike actually traveled. Think of it that way. Is the radius of the circle times the angular velocity omega. So they are related, like the angle and the radius and the circumference of circles are all related geometrically. The same thing is going to happen with the equations in physics. So here's a quick example. So we're going to imagine we have a carousel with 2 rows of horses, an inner row and an outer row. The outer row has a radius of 4 meters, and the inner row has a radius of 2 meters. Carousel is going to make 2 revolutions every minute. And our first question is, what's the angular speed of the carousel? We know the radius, and we know that the angular speed is 2 revolutions per minute. That's what they gave us in the problem. But we need to change it into radians per second. So 2 times around a circle, 2 revolutions, is 4 pi. And 1 minute is 60 seconds. So when you do that math, you get 0.21 radians per second. So it's more of a conversion than an actual calculation in this sense. And then the next question is, what's the tangential speed of a horse on the outer ring of the carousel? So how much distance is that horse actually covering? Velocity is radius times the angular speed. So we have 2 meters as our radius and 0.21 radians per second that we found in the previous part of this problem. And you end up with 0.42 meters per second. The radians just fall out. They're just kind of a placekeeper to let us know that we're in circular mode when we're using omega. So that's your example. Good luck. Bye-bye.